Okay, Assalamualaikum. We continue with the third part of this chapter number 6. That is the assembly of microtubule, or how we can make, or how the cell make the highway for transportation of the protein or the information. Okay, so here microtubule, so one of fundamental component of the eukaryotic cytoskeleton, the highway. Okay, so the primary structure element of cilia and flagella. Okay, so this also you can see that the in the next picture. Okay, so what are microtubules? So microtubules are hollow. Okay, it is in cylindrical structure and approximately 30 nanometer in diameter. So from a tubulin, a dimeric protein composed of two similar 55 kilodalton subunit known as alpha tubulin and beta tubulin. Okay, so dia macam dia ada dua benang, merah dan biru. So it bind together to make this microtubule. Okay, so these are the examples. So it's microtubule. So we can see that the line, this line is the microtubule. Okay, and this one are the microtubule. Okay, so these are for flagella. And these are the shape. Okay, you can see that. So microtubule may be viewed as consisting of 13 parallel but staggered photofilament filament of alternating alpha tubulin and beta tubulin. Okay, so we can see that here alpha merah, benang merah, beta benang, let's say benang biru. So combine together to become this microtubule. Okay, so you can see that these are 1, 2, 3, 4, 5, 6, 7, 8. Okay, and these are the 13 parallels. 1, 2, 3, 4, and 5. So we have 13 parallel. Very good. Okay, so we have the N. Okay, so minus terminal and plus terminal. So the end of the microtubule at which growth occur is the plus N. Okay, so these are the plus N. So all the dimer will, or all the protein will attach here to make it longer and longer. And the minus 1 will, the protein or the dimer will dissociate and detach from this microtubule. Okay, so microtubule in vitro carry out a GTP dependent process called thread milling, in which tubulin dimer are added to the plus and at about the same rate at which the dimer are removed from the minus n. Okay, so here we can see that this one dimer can attach back when it is in plus n. Okay, so we can move around around. Okay, so ini macam landasan kereta api, kita ambil yang belakang, kita sambung ke depan, ambil yang belakang, sambung ke depan, again and again. So this microtubule or the landasan kereta api akan boleh menuju ke depan. Okay, so these are the theoretical growth of microtubule. Okay, so here if we add the addition of subunit x1 plus 1 equal to x1 plus a. Okay, so here if we have this x1, these are x1, we add this x, so it become x1 plus 1. Okay, and if the complete collapse or if stop the growth, so a or complete collapse meaning that the tubulin already dissociate. Okay, so we have x1 plus 1 equal to 0. So there will be no more microtubule. Okay, so the total subunit is xi plus 1 equal to r xi plus a. Okay, so these are the probability p is 0 if s greater than p, random number of 0 to 1, probability of addition of tubulin. Okay, so whether it will add or it will not add. Okay, so this one will add and this one will be complete collapse. Okay, so we can see that whether it can the microtubule can grow very fast or grow very slow or will not grow uh, any more. Okay, so we can get this from this equation. Okay, so the phase transition behavior of the system in that certain lead to overall disassembly and largely a full of tubulin dimer, while other conditions promote self-assembly of tubulin and empty. Okay, so we have in the solvent or in our body, we have the free tubulin and the tubulin that already associate and become the microtubule. Okay, phase of empty polymerization are determined largely by temperature and concentration of the tubulin. Okay, so we can see here the uh, let's say if we increase the suitable temperature, so we're going to have fast production of microtubule, and also if we increase the concentration of tubulin, so it is much faster for tubulin to do the microtubule. Okay, okay, so we have this phase. Okay, non-disassembly of microtubule. So the first one, microtubule assemble but not nucleate. Okay, so here this one meaning that the microtubule, the tubulin can attach and detach from this microtubule. Okay, and this one empty. The second one empty nucleate and assemble. So meaning that it will be very strong uh, binding, so it can grow the microtubule. Okay, so dynamic instability. So here we can see that microtubule are growing in the intermediate vicinity of other empty that are. Okay, so yang dissociate ni, tubulin yang dissociate ni akan bergabung dengan microtubule yang sedang membesar. Okay, so these are the reaction. Okay, MTN plus TGP equal MTN plus 1 addition. MTN, these are the nucleation, and this one is the dissociate. Okay, so tubulin ni bila kita dapat GTCP, so we are going to get back this tubulin GDP and the temperature. Okay, so these are the reaction for the temperature. If we have this temperature Ki and plus 1 dGdP. Okay, so we have this value. Okay, so we have again the tubulin, not a microtubule. Okay, so here these are the picture of this assembly. Okay, so these are assembly confirmation, and it can disassemble become like this. Okay, so this one when binding already cut out from this molecule. Okay, and the assembly of this microtubule, okay, using this guanosine 5 monosphate. Okay, Okay, so these are the tubulin, uh, one of the tubulin. So you can see that it will do this uh, binding again and again, minus and plus side, so become the micro tubule. Okay, so these are the production of micro tubule. Okay, so here one of the example of the microtubule says, so we have actin filament. So the actin is the principal component of thin filament. So G actin is the globular protein, and F actin is fibrous protein. Okay, so you can see here uh, globular globular protein. Okay. Okay, so here these are the again the reaction or the model. So from this A okay, so we have GMP, this one. Okay, GMP. So let's say GMP plus GMP become microtubule. So this GMP attached to microtubule become the, the second microtubule again and again and again and again. So it become longer and longer and longer. Okay, so here you can see that the the rate constant is 10 micromolar per second. Okay, and this the rate of dissociation is 10 to the power of 6 uh, molar micromolar per second. Okay, 10. So here we can see T minus 4, 0.7. So we can see that when this one, so it is easier for uh, this reaction from A4 becoming A plus A3 back, but when it become A plus A4 equal to N, you can see that all are moving from the left to the right. Okay, so these are the concentration of all longer filament. Okay, so these are the dependence of, okay, so depend on the average length of the active filament on the PTR minimal concentration. So the acting filament much longer, so the rate of dissociation will be become 0. So, okay, the active monomer concentration during employment varied as indicated. Okay, so the active monomer, so panjang 1, panjang 2, panjang 3, panjang 4 berlainan. So you can see that, but at after some time it's going to become the saturate. So this one single gel filter acting, double gel filter acting. So these are uh, the length of the acting that we can produce. Okay, so here these are 200 and 2500 uh, molecule attached together to become a acting filament. Okay, so we can modify this acting filament by changing the concentration. Okay, so here we can see A plus A4, N plus N. So Ka is the annealing rate or the assembly rate, association rate, and Kf is dissociation rate. So N. So the rate of change is dN over dt, K plus A4 minus AN2 minus KFN. So assemble this one using this one. So this is might be quite wrong. We can check from our textbook. Okay, so we can see the rate change of this uh, concentration of certain length of actin. Okay, so after we can observe that the rate of annealing goes down when the filament become longer. Why? Because it will need the tubulin need to move more further to find the binding site. Okay, so become annealing goes down when filament become longer. Okay, so macam kita ada, contohnya kita ada 100 kursi. Okay, kursi nombor 1, 2 tu senang dipenuhi. Kursi yang nombor 100 tu, untuk sampai ke kursi nombor 1, kita akan ambil masa untuk sampai ke kursi nombor 100. Okay, so meaning that here KA is diffusion limited association. Okay, so the transverse diffusion is controlled by the mass of the polymer and the density of the polymer network, but the diffusion constant along the tube is inversely proportional to the length of the filament of the form. Okay, so these are the diffusion constant depend on the length of the filament. So eta is the friction coefficient. So to find the K, the rate constant of annealing, Ka equal to either this equation or this equation, Ka prime over L. Okay, so this Ka prime over L is the rate constant or the diffusion constant before this, meaning that these are Ki plus Ki plus I equal to I plus Ki. Okay, so these are for Ki and these are Ki plus I. Okay, the length or the long of the length of the acting or the filament. Okay, so these are the dissociation rate. Number of rod within the distance B of given rod is BL squared to N. Okay, so B are uh, the distance, L is the length of the long of the molecule. Okay, so let's say the tubulin, and N is the uh,